Okay, everyone. Today we're going to go over your continue on with the acceleration notes. At this point, we're going to talk about acceleration and distance. One of the interesting parts with acceleration is whenever we are accelerating, that means that we are getting faster. Every single second we're undergoing that period of acceleration. Our velocity is going to either increase, it is going to decrease, or possibly we could be changing direction. Now, when we are changing our speed, that also means that at the exact same moment, we are changing how far we can go in any given second. Like if I go 1 meter per second, it means in 1 second I can go 1 meter. But when I go 2 meters per second, now I'm going 2 meters, and then I'm going 3, and then I'm going 4, and I'm getting faster and I'm able to cover much more distance. And there are equations that we can use to help us model that behavior and figure out how far an object will travel while it's accelerating. And we can use that to determine how far it's going to go for the distance or how quickly the object is accelerating. We'll end up having a new equation here. Now, this might look like it's long, but we're really only going to do one problem, and then we're going to make it much easier. But the distance is equal to your initial velocity multiplied by your time, added to 1/2 of the acceleration multiplied by your time squared. And all the biggest part is making sure that we're identifying our variables correctly. We plug into a calculator, and all you have to do is type in to see what your answer will be. So we'll go through and do a couple examples, and that'll be it for the video, today's video. All right, I'm going to switch over to my other program so I'm able to write. So with this problem, car is traveling at a speed of 1 meter per second. That is our initial velocity, 1m/s. It accelerates at a rate of 2 meters per second squared. These are the units that we have for acceleration, 2m/s squared. And it takes a total of 3 seconds. How far, that's asking me for distance, will the car travel? Since I have an initial velocity, this equation VIT plus 1/2 AT squared, when I plug in my numbers, D equals initial velocity, 1, my time, 3, plus 1 divided by 2. I usually, instead of leaving that as a fraction, I always just end up writing down 0.5. The acceleration over here, 2. And my time again is 3. Now, be very careful because only this, the time, is squared, nothing else. Now, I can go through and I can simplify 1 times 3, or I can even go in and I can just enter this in the calculator all that I want to. I have always been taught when I'm plugging in numbers to always plug inside of parentheses. If there is no symbol between two variables, that means that it's implied that it is multiplication. So I'm going to take 1 times 3. That gives me 3. I'm going to add it, this whole term, I just want to type in my calculator. 0.5 times 2 times 3 squared equals. And that's going to give me a total of 9. Now, instead of putting times in between, I can also put parentheses. Oops. There, 0.5, another parenthesis, 2, another parenthesis, 3 squared equals. And again, that's going to give me 9. It gives me the same thing. Then I just need to add those two together. My total distance then is a total of 12 meters. So even though we might have an initial velocity, all we have to do is take the initial velocity and multiply by the time. It's just one little extra step. Now, we don't always have an initial velocity. In fact, most of the time, you're not going to have an initial velocity. So what happens if we don't have one? Well, if I have 0 as my initial velocity, when I take 0 times the time, It doesn't matter what any time I happen to have. This whole term is going to end up being 0, and that goes away. So what that really leaves me with is just d equals 1/2 multiplied by the acceleration multiplied by the time squared. Or I kind of don't typically leave that 1/2. I typically write it in class as d equals 0.5 at squared. Okay. Go over the example problems here. Car starts from rest. If it's starting from rest, that means VI is 0 meters per second. It accelerates at a rate 5 meters per second squared. That's my acceleration. A total of 4 seconds. How far does the car travel? Okay. With no initial velocity, d equals 0.5 at squared. And this is actually the version of the equation I'll have in your form listed at the top for you guys. From here, I just want to plug in 0.5, acceleration 5, the time 4, and don't forget about your square. That's the most common mistake I see kids in class make every single year. I'm going to multiply those numbers together. I want to make sure that I don't forget about the square. And when I do, distance is equal to 40 meters. Okay. Next example, Maddox starts from rest, means VI is 0. Accelerates at a rate of 3 meters per second squared. Meters per second squared is always my acceleration, and did this for a total of 10 seconds. How far did it go? No initial velocity. D is 0.5 at squared. 0.5 stays the same. Acceleration is 3. Time is 10. And I want to type that in my calculator. 0.5 times 3 times 10 squared. D is equal to 150 meters. Now, we don't always just solve for the distance. Maybe sometimes I want to solve for the acceleration. With our initial velocity as 0, when I rearrange the equation for a different variable, this ends up being the other version of the equation too. Now, just like with the standard equation for acceleration with the final velocity, the initial, and the time like we were doing last week, I will give you guys each version of the equation, and basically you will just be responsible for plugging it into the calculator correctly. Okay. But all I have to do is take 2 times the distance traveled divided by the time squared. Okay. So, going over the examples here, almost done. Car starts from rest. VI is 0 meters per second. Speeds up for 5 seconds. Seconds measures time. While traveling 40 meters. At what rate did the car accelerate? And it's also asking for what is the final velocity. This is actually asking for 2 different questions. Okay. Since I'm asked to solve for acceleration, this is the version of the equation I want to use, the one that has my variable all by itself on one side of the equation. I'm going to write it down, 2d divided by t squared, plugging in 2 times the distance of 40 divided by the time squared. Okay. Now, even though maybe you have a calculator with a fraction button, you can use it. But kids are always like, where's the fraction button? A fraction is the top divided by the bottom. So I'm going to take 2, multiplying by 40, dividing by what's on the bottom, 5 squared. I'm pressing the square before equaling because I want to square the bottom. I don't want to square the whole thing. My answer then is 3.2, and we measure acceleration in meters per second squared.
Good morning, please pardon the interruption. Teachers, please check your most recent email from Mrs. Lynn. Thank you.
Okay, next. When we're solving for the final velocity, the final velocity is equal to the initial plus the acceleration multiplied by the time. This was an equation from last week. We're still going to be using this equation pretty much each problem with this once you guys get started on your actual problems. You're going to be plugging in. 0 is our initial velocity. When we solve for the acceleration, we have to use that value. This has to be used down here for the second part. When we're finding distance first, they will give us the acceleration and we don't have to use this term. But the acceleration is 3.2. Our time was 5 seconds. So I want to take 0, which I can ignore. I'm going to add it to 3.2 times 5, and that's going to give me VF is 16 meters per second. Next example, Charlotte starts from rest. Starting from rest means VI is 0 meters per second. Runs for a total of 15 meters. Meters measures a distance and does this in a total of 10 seconds. Seconds measures a time. What is her acceleration? What is the final velocity? Okay. So first up, I'm taking a look. If I'm solving for A, I want to use this equation. If I'm solving for D, I want to use this equation. This problem, I'm solving for A, so I'm using the one that has A by itself. A equals 2D divided by T squared. Plugging in my numbers, 2, how far did it go? It went 15. Divided by, what was my time? 10 squared. 2 times 15 divided by 10 squared equals 0.3 meters per second squared. And then to find the second part, what is Charlotte's final velocity? It's VI plus AT. VI is 0. The acceleration we just found, 0.3. And our time is 10 seconds. When I take 0.3, I multiply by 10. That's going to give me a total of 3 meters per second is my final velocity. Okay. And our last example from this section of our notes. Maddox starts from rest. VI is 0 meters per second. Accelerates at a rate of 4 meters per second squared. Meters per second squared, that is an acceleration. Again, you can use your units to help you identify your numbers. Also, typically if you read the problem, it usually says it right beforehand. It accelerates at this rate. It does this for 15 seconds. That's our time. How far? How far asks for distance. And what is the final velocity? So another problem where I'm solving for distance. If I'm solving for D, that's the one that has D by itself, 0.5 AT squared. Plugging in my values, 0.5 times 4 times 15 squared. I want to plug that in my calculator. That gives me a total of 450 meters. Solving for the final velocity. I didn't have to solve for A. All of this just happens to be over here in my data table. Vf is 0 is our initial velocity. Our acceleration is 4, and our time is 15. When I take 4 times 15, that's going to give me a total of 60 meters per second. And that's how we end up going through and solving our examples. All right. And that concludes today's video.